Good afternoon. We'll go ahead and get started. First, I want to remind people to check in. So at each entrance, there's a QR code if you haven't already checked in, or maybe you can do it through the app, the Campus Groups app. But it helps us justify the food budget. So if you want to keep eating the food, then please register so we know how many folks are here. So it's my pleasure to introduce Professor Ling Zang from University of Utah. He's flew all the way across the country today, the 1-hour flight to get here. So from our nearest neighbor, we're delighted to have him. Professor Zhang is a member of numerous prestigious scientific societies and has won several awards and has a passion for startups and inventing. And today we're going to hear about their work on chemical sensing. And so I'll leave it to you.
Well, thank you, Alden. Everybody hear me well? It's really good to show me energy from Friday anyway. Well, thank you for coming. It's Friday afternoon. I'll try my best to make it. It's not so bored anyway. So it's really a great pleasure to visit here. So I learned a lot. Excellent research program from thin film to DNA computing and all kind of things in terms of nanomaterial, nanotechnology. So today, I like to share something from my lab, mostly focused on chemical sensors. And you see some of the materials quite much relevant to nanomaterials. So we do have a lot of mutual interest, not just between the two campers, between a lot of colleagues here. I hope we can initiate some collaboration in the future anyway. So I was told to spend about 40 minutes to finish my talk, right? So I will encourage you to raise your hand for any questions. Otherwise, I'll keep talking 3 hours, okay? So, so to that regard, especially for the young audience here, so in addition to the fundamental science relevant to chemical sensor, I'm also gonna talk quite a bit, relevant to the real applications. So how the chemical sensor can be used to serve, to support, to solve the problem currently in the health environment or even the public safety, right? Hopefully, kind of good story we can wrap up today. And so here it is. So as Elton said, I mean, really long trip, just barely 1 hour's flight. So I was surprised, so close, right? We are here and you guys are over here. So even though it's my first time to visit here, again, it's beautiful campus, I really love it. But you know what? I believe I flew over Boise many times whenever I travel to Seattle. Okay, it's on the flight lines anyway. So hopefully we can visit quite often. I will also welcome you guys to visit Salt Lake City, not just ski. I know you guys have ski area here, quite beautiful, but some other reason, right? So we can do something together. So here's my campus. So it's kind of bragging, right? I know you have beautiful campus. So this our building is relatively new building, but on the other hand, I really impressed by this new building. It's just awesome. Not only the facility, but also all the infrastructure going on over here. And so our building is relatively new on this old campus, even though it's 13 years old already, but relatively old compared to most of the engineering building on that campus anyway. So we are part of the USTAR program, standing for USTAR Science Technology Initiative. So why I'm mentioning that, because the state put quite a bit budget to build this building, in addition to some private funding anyway. So our lab located on the 5th floor, and this is not my home department. This kind of USTAR program, somehow like an advanced institute, incorporating all kind of people with crazy mind. So we're working together. So for example, on the 5th floor, we have people from medical school, from pharmaceutical, from ECE, from whatever, right? I'm from chemistry and material science anyway. So the USTAR program aimed to promote the local high technology economic development, right? Utah is maybe a little bit larger than Idaho, but still a small state, right? We don't compete manufacturing with the East Coast or West Coast, those kind of big industry states. So that's why back in 2007. So the whole state initiated a new program, how to further boost the local economics through the high technology, especially nanotechnology, right? So that's how the USTAR program came from. Anyhow, so now back to chemical sensors, right? So we start the chemical sensor all the way back to more than 20 years ago from the molecules, right? I know some of you work on molecules, different type molecules, especially the molecule giving fluorescence. So we design all this molecule. I'm going to show some example a little bit later, all right? So later on, we find, well, if you want to further increase the performance of your sensor, you might want to move on beyond this molecule itself. So how to assemble this molecule in somehow organized structure to leverage the amplified fluorescent quenching efficiency, right? Somehow like you have a wire better than a single dot, right? And even later on, so we can develop some specific one-dimensional nanowire composed of the columnar stacking of the molecules. So from that case, not only the optical signal can be amplified, but also the electrical conductivity leveraging on the charge transfer can also be incorporated to further increase the performance of the sensor anyway. So that's a timeline also can be regarded as the R&D technology advancement lines. So that's something I'm going to cover as a major topic of today, of course, along with some real applications. So this one slide summarizes our past or maybe somehow recent research effort in relevant to the commercialization effort. So on the left side is really cover about the nanofiber materials used as a gas sensor for detection of all kind of chemicals, including explosives. On the right side is totally different approach in the water solution, the liquid phase, all based on molecular probe. So how you can leverage the fluorescence modulation to enable detection of metal pollution or even the PFAS chemical pollution, one of the current global concern. So as a brief summary, long story short, we publish not just papers, we also finish up and file a lot of patents. Along with this, we also have 3 startup formulate and from the university. So all this combined together, again, as I mentioned, so the aim and the goal here is to trying to address a major challenge and a problem currently faced or encountered in the health or environmental and public safety domains. So along with this, I want to say something about my university. So about 20 years ago, I moved to that campus. One of the personal reasons I really enjoy the culture of the entrepreneurship, tech transfer, and more than that is a huge effort behind the university. They provide a lot of support to the faculty members to initiate this kind of effort. So with that, I do have a very important slides for your campus here, right? So I learned you guys also have a very good and strong technology transfer team. You can see all the name here. I'm not sure Sarah here yet. Here, oh, here we go. So good to see you guys. So you have a barcode. Feel free to scan or get to the website. You can learn more about that. So in case you have some crazy ideas, smart idea, whatever innovation in mind, even students, right? So I think you're welcome to contact this team. So you will get a lot of opportunity, I think, support in the future anyway, right? With that, back to sensor, right? So I always come up with a slide, right? Some people ask me, not just from here, this today, so some other people ask me all that kind of questions. So what would be the fundamental or basic criteria for sensor, right? We're talking about chemical sensor, physical sensor, all kind of things. So I try my best to come up with this 6S, right? Actually 5S plus $1 all right? So among all this, I think the top 2 can be considered as a primary requirement. If you ever try to develop a new sensor, if it's not sensitive enough or not selected enough, forget about it, right? You don't worry about the speed, small or cost. So the top 2 is really a primary requirement. Actually, if you got a chance to review or to read or look through some publication in the future, keep in mind this top 2 criteria, right? Anyhow, So what's a sensor? How to define a chemical sensor, right? So in general, you can consider any type of material to be used as a sensor. Could be molecules, could be nanomaterial like quantum dots, could be a nanowire, could be a thin film, right? We have a very strong thin film program over here. So you guys have a lot of opportunity to learn from there anyway. So in this case, if you have some target analyte, right? Could be in gas phase, could be in liquid phase, could be some pollutant, could be some danger chemicals. So whenever this sensor got interact with your analyte, right, you're gonna see some change, okay? So very often, maybe the color of your material, your thin film, your material got changed from, blue to pink. So that color change can be even visioned by your eyes, right? That's a sensor, that's a response, okay? So in this case, you can define this colorimetric sensor, right? It's just based on color change, right? So, and beyond that, right, some of the material may be glowing, right? Halloween time is coming, right? You know that. Playing with black light, you see some glowing crazy, right? So this glowing material we call fluorescent materials. So in that case, you have some analyte got interact or exposed to the sensor, you're gonna see the fluorescence maybe turn on. For example, in our lab, we have this magic fluorescence molecules suspended in solution. You see it's dark, right? Put black light on it, it's dark, not glowing at all. But on the other hand, if you have something dirt or something bad in the solution, you know what happened? You turn on the green fluorescence, right? That's called fluorescent turn on sensor, right? Or turn on mode or on mode. So on the other hand, totally opposite way, right? You might start with something is glowing by itself, right, in the pristine state. But if you have something, again, pollution or chemical danger present, you will find the luminescence all dimmed or disappeared. So again, you can see, depending how much intensity of the emission dimmed or decreased, you will be able to tell how much of the target analyte present in the system, right? So, and now, why not combine these two together? Right? Not just simply on or off, right? You might be able to see something change in the color. Initially, maybe, I don't know what this color is, purple, right? If you have something target analyte present around, you will see the color change from purple to green, right? Not just to disappear, not simply on, it's change of the color. In this case, we call ratiometric sensor, all right? So you see all this combined together, we call optical mode, either by color change or luminescence change, right? But another alternative way is to monitor the electrical signal, right? You might have your sensor material is semiconductor, or maybe something relevant to that as a thin film, or again, quantum materials, whatever it is, right? You might be able to monitor the resistance, right? I do have a chance to interact with several colleagues here. They work in the relevant field, right? So in that case, by modulating the current or resistance change upon exposure to the chemicals, you will be able to develop a chemi-resistive sensor. That's chemical resistance combined together, right? Similarly, you might be able to combine the materials into electrochemical system. You got, by coating on the electrode, for example, you can develop electrochemical sensor, right? So, and for all this type of sensor, you will be able to detect all kind of chemicals, right? Could be in the gas phase, could be in the liquid, covering all this different type of sensors. So in my lab, we used to be working quite a bit for explosive, toxic chemicals, or even the chemical warfare agent, really nasty stuff. And there's a sponsor project from DoD, Defense, and Department of Defense and Department of Homeland Security about 10 years ago. And along that, you can also detect heavy metal pollution in the water, and also through collaboration with my colleague in nuclear engineering department. So we also developed some radiation sensor for this kind of specific detection, not just chemicals, but something beyond. So again, back to the comment I made earlier. So whenever you're trying to consider a new type of sensor, so the sensitivity and selectivity always remain as the two top primary requirement or criteria. So with that in mind, let me show you, go through very quick some of the real case study from our lab in past, I don't know, 20 plus years to trying to show, especially a student here, so how the different mode of sensor I just described works in the real case, right? The first one is colorimetric sensor. So it's very simple. Everything is so low cost. This is a paper tower. It's the same thing you use in kitchen every day. So we can coat this paper tower with this specific molecules. It's titanium complex. Everything is colorless, same color as the paper tower itself. But if you expose this magic paper tower to hydrogen peroxide, okay, so you're going to see the color change from nothing to yellowish, right? Imagine that if you have this specific paper tower in the room somewhere, you will be able to tell, detect hydrogen peroxide. All right. So, and later on, this type of simple sensor has been adapted through collaboration with colleague from Navy Research Lab in Washington, D.C., to be incorporated in the very miniaturized specific optical devices for whatever the application, right, in the military. And similarly, for the fluorescent turn-on sensor, again for hydrogen peroxide, so we have synthesized this specific molecules, right? By itself, it's not glowing at all, totally dark. Again, if you expose to hydrogen peroxide in solution, you see strong yellow or greenish emission come up, right? Depending how much emission you turn on, you observe in terms of increase in emission intensity, you will be able to tell how much of the hydrogen peroxide present, right? It's very quantitative. So with the detection limit all the way down to 5 ppb in gas phase, that's pretty amazing, okay? So more than that, back to the selectivity, one of the two criteria I mentioned, right? So yeah, except for the hydrogen peroxide, nothing else from the common organic solvent or species, they don't turn on anything. So show perfect selectivity. So some of you may be curious why you bother hydrogen peroxide. It's not really toxic, right? We use a lot every day at home even. So, but on the other hand, if you think about the industry application of hydrogen peroxide has been used extensively in all this biodetermination or sterilization in health, medical, in pharmaceutical industry. So we do need some way to quickly monitor the level, right? Because if you have hydrogen peroxide extract at too high level, it's still not good for the health. More than that, back to my Homeland Security project we ran before, right? Not trying to scare you guys, right? Hydrogen peroxide is a key precursor for making explosives. I won't tell you the recipe, but it is the case, right? So let's give a way to make our reliable sensor to monitor this explosive before it's getting too bad, right? So, and if you Google this news, right, you know this happened years ago, right? This kind of explosive happened. It's not good, right? So it's very critical to find some good sensor, reliable sensor to be used for this kind of scenarios. Okay, so trying to switch the gear to the water phase, and here comes the quenching mode or turn off mode for fluorescent sensor. So again, this molecule sensor, right, itself is in the clean water, so it show very strong green fluorescence. But if you have, heavy metal like a mercury, mercury is very bad. And locally there, we face a critical issue in Great Salt Lake. We do have pretty serious issue about the mercury pollution through the food chain, right? Anyway, so that's some of the reason we initiated this project a long time ago. And through this, dimming out the emission, you will be able to create the calibration curve, right? If you have a little bit of knowledge on the analytical chemistry, we do need calibration curve. And through this simple measurement, we developed this kind of handheld device. And along with some, very basic, chemicals, pipette, whatever, cuvette, wasting deposit, whatever, combine this into a small package, portable package of detection kit. So it's pretty useful for the water monitoring with a very quick answer anyway. So this was technology licensed and developed by Metallo Sensor, one of the 3 companies we developed. So again, selectivity, right? Other than mercury, any other common metal do not show anything. So perfect selectivity as well, because you don't want to generate positive to be scary, right? Anyway, so because of those reasons, locally, again, as I mentioned, right, Great Salt Lake area, we are all concerned about mercury pollution because, if you know, Great Salt Lake is a kind of Dead Sea, right? It's Dead Sea. It's pretty crucial for the local environment. So this type of thing trigger quite a bit of attention from the local areas as covered by the Delaware news locally. So now, turn on sensor, right? Turn off sensor, all based on luminescence monitoring. So we have this ratiometric sensor combining both mode, right? So this molecules, right? You don't need to know detail about this organic chemistry in case you really want to know this core synthesis behind, okay? So by itself, this molecule give a kind of reddish emission with a long wavelength around 700 nanometer. But if you expose to mercury, not mercury here, is cadmium, right? Another metal pollution. You're going to generate a beautiful yellowish emission with the original red emission got decreased. This is ratiometrics, right? One decrease, the other one increase. So, and another one, also based on ratiometric mode, but not for chemicals, but for radioactive species, is especially for gamma ray. So long story short, this kind of project initiated through collaboration with my medical colleague, because if you know a little bit, we have Huntsman Cancer Institute in that city is one of the top of the world. And part of the cancer therapy is based on radiotherapy with gamma ray. So you can imagine why gamma ray is so powerful to kill the cancer, because they're powerful, but also they are powerful to help to normal cells, right? You want to control the level, the dose of the gamma ray exactly and precisely every time to be used for the patient. And that's the reason we see this kind of requirement and demand to develop a sensor which can be used for regular and quick calibration of the gamma ray. Okay, long story short, again, so this would be a ratiometric sensor, right? If you got no gamma ray is bluish emission, but if you have gamma ray exposed, you got to change the color from bluish to a greenish, right? This typical ratiometric sensor. But more than that, as a material scientist, I got excited. It kind of byproduct from that project. Not only the ratiometric sensor based on fluorescence, but at the very end, after exposed to gamma ray, you form this beautiful fibrous structures. Initially, it's just solution, right? It's just molecules. So what happened to the nanofibers? It is a self-assembly. The molecules self-assemble by themselves after gamma ray irradiation. So now, if you consider this all as wires, right? You can deposit this between two electrodes and form a circuit, right? You can measure the electrical signal to develop an electrical mode sensor, kind of 2-in-1, right? Maybe 3-in-1 device, all right? So we published the paper in 2015. If you want to know, you can go to that paper. But now let me switch the gear to nanofibers, right? So nanofibers itself as the materials, it will be really intriguing and interesting for many reasons. So we spent a lot of years, a lot of time to trying to control the self-assembly of the molecules into different geometry and different size in terms of one-dimensional nanomaterials, all right? So we have published 2 review papers, actually 3 from 2008 and the very recent one, 2015. You can go through that's kind of a paper cover more story about this. But again, back to this nanofibers, right? Okay. So as I mentioned, so molecules could be luminescent, but the material also can be luminescent, right? Especially down to the nanofiber structure, right? So for example, this nanofiber showing very strong reddish luminescence, and some others showing very beautiful bluish, and some other maybe green, right? We cover 3 primary colors. Some of my colleagues were there asking me, can you make a LED, right? Why make a TV, right? But that's not my favorite field anyway, so it's beyond my expertise. I'm still a sensor guy, right? I'm trying to leverage the different color to be used for chemical sensors. Why? As I talked to some of the colleagues today, it's really about the excitone diffusion. If you have this nanofiber composed of a single crystal structure with all the molecules organized so well, you're going to have a perfect electronic interaction in between the molecules, right? Like a domino stuff, right? The molecules that communicate each other. So this will be the case. You have the very long fiber, right? The emission you can see from the color or from the whole body of the fiber, but pay a little bit attention to the very end, right? You see the spot like a nanofiber flashlight. Okay, why you have a little bit more concentrated light at the very end? Because the acetone, the excited state, can be transferred all the way to the end. So why not take advantage of this, right? So if you look at this scheme, right, if you got low excited state, okay, so the emission will be coming from here, but if you got long-range acetone diffusion, you're going to provide more chance for the quenching efficiency. To explain that before that, we have paper published in 2011 focus on the physics of the excited state. Sometimes even beyond microscope as a chemist anyway. So that's kind of experiment prove at the room temperature you have efficient acetone excited state transformation, transport, okay? So taking advantage of this efficient long-range acetone or excited state transport, so back to this design principle of the chemical sensor, as I mentioned earlier. So that will be the second stage of the material development from my lab to enhance the efficiency or performance of the sensor. So I try my best to come up with this animation. Hopefully it works. Okay, so if you excited the nanofiber, just like you excite the molecule, as I mentioned earlier, right? You're going to generate emission from this local area, right? From the excited state. And if you have a chemical state right at the position, you will be able to get the quenching, right? Dimming of the emission. But the challenge is, if you have a very dilute species or very few chemicals to be detected, very low possibility you're going to have the molecule stick to the right position. Right? If not, the emission going to still keeps on. That means you're going to miss that molecule to be detected. So, but on the other hand, if the whole nanofiber is so organized, you're going to have very long-range efficient acetone diffusion. In that case, the acetone is going to diffuse all the way through the fiber, right? Think about it. It's really about playing possibility, right? If you have the acetone diffusion in the long-range distance, you will have more chance to get this guy to be trapped, to be captured, right? So that's exactly the case. So within this long-range diffusion, if you have species like TNT, right? This is always our favorite molecule to be detected. So, and on the way of the diffusion of the acetone, right? Let's play again, right? So this guy can be trapped because TNT is there. It's a bad guy, right? So whenever it's trapped by TNT through the interfacial electron transfer, whatever, okay? So, and you will have this emission quenched. So you see the whole process is really about playing probability, okay? Through this long-range diffusion of the excited state, you will have more chance for the emission got be quenched to enhance the performance of the sensor, right? So now the real story, okay? So this is a paper we published in 2007, quite a year ago, right? So in this case, you can see without TNT, you see the emission pretty strong. But if you have TNT, even though PBB level, later on we further improved down to 10 PBT level in gas phase, it's just impressive. So within seconds, you can see the emission got quenched very quick, right? So this is the story happened in 2007. And a little bit later, okay, actually just 1 year later, we have another paper coming out, again playing different luminescence but different fibers. And you see in the clean air, all the fiber glowing crazily in the reddish color and the dark. But if you have some, amines, we call amines ammonia. But in the real case, some of the nasty chemicals, the illegal drug, they are all amines, okay? They are all amines. So what happens if you have this amines around? So you will be able to see how quick this type of glowing can be dimmed when the evil thing is coming around.
This glowing red clump of nanofibers is the key.
As you can see, fluorescence is being.
So this guy trying to blow some amine with a syringe. You see the color dim right away. You see that, Vic?
When the glow is gone, the fibers have sensed the meth simulant. Each nanofiber.
Well, you probably realize the voice much better than mine because they're from the TV channel anyway, not mine, okay? So, okay, so that's about nanofiber. It's a lot of beauty stuff. I mean, even for the electron mode, right? Later we see, well, it's, optical amplification through the isotope, transport. It's pretty cool. So how about the electricity, right? How about the electrical mode, right? We all know graphite, graphene, right? Why graphite is conductive? Because the layer by layer, you have pi stacking, you have the pi electron can be tunneling, right? So now the same thing, right? If you have the fiber composed of this highly organized pi stacking between the molecules, you will be able to have, again, delocalization of the electrons, right? That's exactly the case, right? If you have a molecule, again, that means donate one electron into one of the molecules in the fiber, so this electron won't be localized. It can be diffused redness around, right, along the fibers. So this gives a chance to monitor the electroconductivity, with response to the surface chemicals. So that's one of the very early stage proof of concept study. If you have a hydrazine, one of the amines is kind of air pollution around, you'll be able to see order of magnitude increase of the connectivity because of this effort, because of this reason, right? So anyhow, so leveraging on this, or combining both optical amplification and the electrical mode sensing, and we came out with this crazy new mode of sensor we call photochemical resistor, basically combining the optical mode and electrical mode together. I think we created this concept, photochemical resistor. Again, this concept published in several papers, including this mini review by American Chemical Society. So long story short here, so why this is so critical? Because we leverage on the excitation of the light, because the light illumination provide extra energy into the fiber to make it possible to detect some of the inert chemicals, right? If without light, you have chemicals stay on the surface, they may initiate enough information or charge transfer around the interface. But if you get the fiber excited, you provide extra energy, right? You're gonna have this charge separation feasible or possible, right? That's kind of a game-changing design principle behind. All right, so again, some real example. So with this combined photochemical resistor mode, so we can have this sensor either detect electron donation chemicals or electron withdrawing chemicals. Right? This maybe sound too much chemistry, but for the first example, you can take the illegal drug. This is the simulant of meth, right? And the lower panel for the electron withdrawing chemicals, you can take explosive, natural explosive as an example, right? So basically, through this same nanofiber, you will be able to detect, distinguish this totally two different type of chemicals. One is drugs, the other one is explosive. One get positive signal, the other one get negative signal because of different electron transfer directions. All right, so, and build upon all this concept proven. So in collaboration with the industry and whatever the partner, we work together trying to push this onto some real application in the market sector, trying to serve different customer. So we fabricate all these different type of nanofiber you can see from the different color and deposit onto the interdigit electrode. So all this fabricated in clean room. Right, you guys also have an awesome clean room here. You can do the same thing, I believe. So with that, you'll be able to see, I'm not sure you can see this. So this the interdigit, many pairs of the finger of electrode. You can see underneath the fiber, you can see the finger of electrode. And above that, you can see the network of nanofibers. Right? So tiny fibers. So to make the image to be viewed better, to see how small the fiber we have. So my former student put his own hair onto the same device. Okay, not for application, just for purpose for presentation. You see how big the human hair compared to the fiber, right? You see tiny, very tiny. So you can see here, not only tiny fiber provide a huge surface, but also at the same time when you have the fiber forming a super network, you provide a continuous porosity. It's perfect for gas phase detection because for this detection, we not only need high efficiency, but we also need speed. One of the 6 S I mentioned earlier, right? You need fast, right? And indeed, if you look closer, and you will see the super network. And interestingly, if you compare to the olfactory system of dog nose, you see the similarity. So why dog nose so sensitive? You see the reason from the standpoint of material science, right? So to that regard, I think if you have the chance to fabricate this nanofiber network into a sensor device, I think it's going to function in two purpose, right? One is as a sampling system beyond the sensor itself, right? And this back to an argument or maybe a question from my collaborator, my friend, and my colleague as well. So how sensitive your fiber would be when used in explosive detection in the gas phase? Sometimes I joke back, it depends how much time you allow me to do that, right? You can imagine that. So if you have this kind of like a sponge, right? Sponge, how much water the sponge can detect depends how much time you immerse in the water, right? Same thing. So you can imagine, right? So this type of things will be really awesome. I don't have time to show the video we took in the lab because of the limitation of time today. So you can see if you got this fiber exposed to the illegal drug deposit on some papers, the signal keep growing all the time, even though it's far away from the sensor. So that's telling the sampling side of the nanofibers. But one thing I want to highlight, so because of this efficiency of the nanofiber-based sensor, you can detect the explosive which is not volatile at all, like a rock. We do have some explosive, like military explosive, they're like a rock, they're stable. So like this guy, RTX or PET, and they have vapor pressure like PBT level, almost nothing, almost nothing. PBT means 10 to minus 12, right? So even dog cannot smell those stuff, right? But under the nanofiber, you can detect the signal, right? This data, again, from verified and from Navy Research Lab anyway. So I think if you're talking about potential or impact to the real world security, I think this solves the problem faced by the dog in the real case. In this case, actually, we do have some, well, not we do, we used to have some collaboration with Homeland Security canine training team, right? Part of the reason is due to the security checking point in the airport, whatever. So the challenge for dog, not only the sensitivity sometime in the summer, and also because of the behavior of the dog, right? Especially in the nasty summertime, like Salt Lake City, we have 100 degrees. I'm not sure here, it's maybe not so bad. The dog won't work after 30 minutes or 1 hour, right? It's got fatigue very quick. You see my point? This is animal, right? This is mammal. Anyhow, but if you have chemical sensor nanofibers, they never got tired anyway, right? See the point? That's different from the dog. Okay, so back to the sensor, the two primary issues. By the way, I think I have 40 minutes. Now it's 35 already, 30, almost there. So sensitivity is very critical, right? Like a nanofiber sensor, we got a very good sensitivity. So because high sensitivity helped prevent the false negative, right? As I mentioned. But on the other hand, selectivity also important, right? Make sure we don't have false positive, right? Because we have so many different types of stuff in the air sometimes. So let's come to the next thing I want to share with you. So to further increase the detection selectivity, or how to make sure your fiber, your sensor, whatever made of, is specific enough to tell the answer only for the target species, not the common stuff, right? So let's come out to the next concept. We got differential sensing by incorporating multiple sensors into our array, okay? So in this case, again, this is an image from the local TV channel. This took beautiful picture anyway. That's why I want to share with you. So 16 different nanofiber. Each of the fibers share the same super network, as I mentioned, right? Sensitivity, no big deal in this case. But the point is, if you combine all these different fibers together, and you're going to generate an array, eventually you're going to provide a fingerprint. You see my point? So each of the fiber are going to create different fingerprint based on the 16 nanofibers. You will be able to tell which is which. Right? That's very critical. And very quick, let me show you the very early study. You have like here, you have 7 different chemicals covering all kind of industry domain. You can use only 5 nanofiber to distinguish them. Even more interesting, we have a local, you guys know Salt Lake City, right? We are very special for essential oil, right? On nutrition, whatever industry. So we do have a very good essential industry over here. So we got some sample, right? There's different type of essential oil. Right? If you got a chance, you know there's different essential oil. And some of them smell similarly, right? Like those grapefruit or yuzu or orange, they're based on the same type of fruit. But under the nanofiber as a nose, we can distinguish them very well, okay? So we're trying to initiate further collaboration to tell them how to realize quality control lines very quick. So that could be a good, cool collaborations. So all this is not invented by me. It's inspired from the nature, right? So we have nose, dog has nose. They all can smell different species. And the 2 people discovered this nose, and actually based on the olfactory protein in the membrane, got Nobel Prize in 2004. Okay, so you see within our nose, we have thousands of different protein function as sensor in the membrane. So you can imagine how powerful this kind of array can do to distinguish different smells. Okay, so following this kind of inspiration, so with our 16 nanofiber array, so we tried our effort to help people to screen the early stage of disease through the breath. Okay, so very quick information. So every breath we make, you spare out thousands of different molecules. We are amazing. We produce molecules, right? So if you can distinguish a specific molecule you generate from your breath, you will be able to detect your health. Okay, that's a very basic principles. And we pick up one of the disease. It's called numerical neurosis. It's a long name. It's the kind of a lung disease, like a cancer of lungs caused by inhalation of the dust. Right? If you got the mining of the silica area, like a rock, stones, you're gonna get some disease called silicosis. All right. The medical name called numerical neurosis. Right? In that case, it's very painful. In a developing country like China, India, they have million people suffering from this disease. At a very later stage, just like a cancer, it's very painful. I don't want to describe that. But the point is, if you can tell the early warning at the early stage, just like many cancers, right, you will be able to have more chance, more options for the medical treatment. So to improve the life quality and disease very quickly. So through our nanofiber sensor, you can see even in the early stage, you will be able to tell the difference. That means with the accuracy, I think around 90%. That's pretty amazing. We published this paper 3 years ago anyway. So still in the early stage, but I think this is a great potential for this fiber-based array for the detections. All right, so I wish I still have several minutes, maybe 5. I want to share the very recent, truly fresh result, okay? Not older than 1 year, all right? On the PFAS detection. I know some of colleagues here, as I learned today, you are interested in PFAS. And PFAS is a forever chemicals. How many of you heard PFAS for students? Wow, it's amazing, right? It's like a joke, right? As I comment, years ago used to be a superstar product from 3M, from DuPont. We know that. I mean, even though nowadays the Teflon non-stick coating of the pen, we still enjoy that. It's perfect material in terms of chemistry, beautiful stability. But now it's like a, in my word, like a rat in the street. Nobody like it anymore because the health risk. So the point is, well, let's just try to scare you guys again. So many different type of PFAS, right? So the reason PFAS is not good because all the hydrogen in the hydrocarbons replaced by fluoride. This kind of replacement makes this molecule so stable, tolerate high temperature, tolerate chemical environment, so stable. That's why forever chemicals, they don't degrade by themselves in the nature. But the point is, as I mentioned, is kind of fluoride chemicals not good for health, as recently confirmed, right? Now the point is how to detect them, how to remove them, how to treat them. And of course, we are sensor people, right? So one of the first people we published barely 1 year ago, I told you it's fresh. So we use this fluorescent turn off mode, as I mentioned earlier, right? The molecule itself is greenish, beautiful color of emission. If you have PFOS, one of the PFAS, the whole emission gonna be dimmed down, right? We know there's PFOS or PFAS inside. And this kind of interaction in between, back to fundamental of chemistry, is coordinated by different type of interactions, right? And due to this multiple interactions mode, so we can approach the selectivity. That's exactly the case. And only respond to PFOS. All the other PFAS are common detergent or whatever chemicals, metals in the water, doesn't matter, right? And similarly, later on, we're trying to push forward. Again, PFAS is a real challenge. And so two major challenge for PFAS detection, okay? One is very low concentration challenge, right? So some area, maybe you have a little bit higher concentration of PFAS, but most of the time, you're talking about PPT level. That's the exact drinking level set up by EPA. 4 PPT for PFOA, PFOS. 4 PPT is almost nothing, as I mentioned earlier, right? So how to detect this low concentration? And second, to target this low concentration, very trace level PFAS in the solution, you need to have some pre-concentration. Even for the EPA verified method, you still need pre-concentration method. Use resin or carbon, whatever the material is. All right. So to keep these two challenges in mind, so we usually develop MOF-based method because MOF can help pre-concentrate the low level of the PFAS in water. At the same time, we can modify the MOF to be a sensor materials back to the knowledge we developed, we create earlier, as I mentioned. So dual function MOF really works. What is MOF, right? It's just a framework composed of metal ions and the organic molecule as a ligand to form this framework, okay? So I bet more people nowadays know MOF because the Nobel Prize announced on Wednesday, right? This Wednesday. So to that regard, so those three guys, right? And for MOF materials, okay? So that's a good reason, right? So some of you, maybe you have not picked up your career yet. So this could be a good area, right, to do. And anyway, so by leveraging the unique feature of MOF, and we developed last year of this MOF, a very specific MOF because the ligand is fluorophore, one of the sensor molecule we used before, but now part of the MOF, right? You see that point? So if you have PFAS, right, got absorbed or captured inside the MOF, the whole MOF can be turned on, back to the same turn on mode as I mentioned, right? So that's the exact case, right? If you don't have anything in the water, the MOF itself keep dark. If you have a little bit PFAS, you're gonna see the turn on of the fluorescent. All right. So, and if you deposit this MOF onto a paper tower, as we mentioned before, low cost, everything, right? And you will be able to further push the detection limit down to PPP level. It's pretty amazing, right? And again, I promise it will be last 2 slides, maybe, I hope. To even further to push the absorption capacity or efficiency of the sensor of the PFAS, you can always do something with the MOF itself. That's another reason, one of the reasons those three guys got recognized for Nobel Prize, because MOF is so flexible and adaptable materials, not only for application, but also for the property and the feature and function modulations. So one of the way is you can do something with the ligand, right? Why not just make the ligand to be positively charged? Okay, so because PFAS is a negative charge, right? Negative, positive, they're gonna attract each other. So very easy, common sense. So you can use this way to further improve the capacity of the absorption of the PFAS, right? Exactly, you can see over here with this simple modification, the capacity of the absorption of the MOF can be much higher than the original MOF itself, even higher than the carbon material we normally used for water purification. And due to this high capacity of the absorption, you can imagine, so the absorption process or response should be very quick, right? if you test with 50 ppb PFOA in water solution, so 99, I won't say 100%, 99% within the error bar can be absorbed within just a few minutes, okay? So now back to sensor, right? Again, the topic today is sensor, right? So through this very quick absorption process, you will be able to have the sensor also respond very, very quick, right? Same thing behind. So to that regard, you can see this. Again, you can monitor the emission from 0 all the way to 5 micromolar concentration of PFAS in the solution. We got beautiful calibration curve, right? Beautiful calibration curve. And because of this huge potential, right? Again, what I show you today is a very fresh result, not comprehensive yet. So, but the potential of MOF, right, as a resonant to the Nobel Prize announcement of 2 days back. So, so MOF would be, in my opinion, at the moment, and I hope, right, would be one of the most promising materials we can enjoy, we can leverage to come up with some solution for the PFAS. It's a global concern, exactly as highlighted in the chemical engineering news not long ago. So they consider the MOF as the material offering something. They don't call it dual function, they call it two offers. When I learned this new release from the editor, as it's a new word to me in English, not my native speaking language anyway. So two offers. And later on I figured out, as I learned from my colleague, it's basically buy one, get one free, right? So MOF is not just sensor, not just the absorption materials, it's also a sensor, right? So anyway, so with that, so I think I need to come up with a promise. It's really last slides. So all this research has been sponsored by different type of federal agency, including the USTAR program from our own state, as well as the current sponsor project from Genentech Corporation. They licensed quite a bit technology from my lab. And also a lot of people working on this in past years. So I don't need to mention all those names. So with that, thank you very much for your attention in the Friday afternoon anyway. So I'm open for any question you want.
How do you tune the selectivity of the nanofibers? You had the slide about the 5 fibers detecting 7 chemicals. How do they do that?
That's very good questions. That's called differential sensing, right? So let me try to describe it in a simple way, if I can. So if you have let's say you have two fibers, right? So you have a chemical coming in, all right? So one sensor got up signal, the other one got negative, okay? You got positive, negative. If you have B coming, maybe both got positive, right? Maybe C coming, you got positive, negative and positive. So basically you have plus minus, plus plus, or minus plus. That's a combination, right? That's how differential sensing works. Okay, you can imagine, right? By playing the math, the more fiber you have, the more up combination you're gonna have. Okay, all right.
Follow up on Jacob's question. Are you functionalizing the fibers to influence those plus and minuses, or is it just intrinsic?
Yeah, I wish I have time to mention that. So each of the fiber have different component or building block molecules. So each of the building block molecule we modify with different functional group for the binding. Exactly. Yeah, that's a primary bottom-up design for the selectivity at the first place.
Thank you. Nice talk. Mike, I have some questions about for these devices when not in use. After you've made an analysis, are they just purged and recycled? Can you reset them? And how would you do that?
Very, very interesting point, especially regarding the practical applications. For the nanofiber sensor for gas phase detection, we have two kind of a scenario to consider. If you have a very volatile gas, right, like a small molecule, target, so because of the volatile, so it can be refreshed or can be blown away by blowing with clean air or nitrogen, right? But sometimes we have some, gas species like TNT or some explosive. They're not so volatile. They're sticky to the surface. So in that case, you might be use some heating. We do have some device with micro heater, circuit behind. So, and a little bit elevated temperature, you will be able to have the nanofiber refresh. But of course, you cannot heat it too much, otherwise the fiber can be destroyed. So, yeah.
Okay, so that would mean that for a field deployment, something like that, you'd have to have a source of purging
Yeah.
material and
Yeah.
yeah, that's a
Yeah,
challenge.
to that regard, I have an interesting story to tell, maybe very quick. So it depends again. So if you use for some, specific case, like chemical warfare agents, those kind of stuff is very restricted and not, allowable, accessible to public. So in that case, whenever it got used one time, the whole thing got destroyed in a specific way. So that's different specific application domain. So we don't need worry about recovery in that case. So.
Maybe last question?
Thank you so much for your talk. My question is regarding the sensitivity. How far from the current water regulations are those sensitivities for the metals? And also, I don't think we have regulations still for PFAS, but how close we are to have a safe water using those sensors?
If I understand your question right, so how far our current sensitivity for PFAS?
For example, for the current regulations establishes some thresholds of concentrations for metals, for organic contaminations.
Right.
And so can we detect until the limit of those thresholds using the sensors that you are developing?
Again, I'm not sure I catch exactly the point you're trying to raise.
For example, let's say for metals, let's say copper. I don't remember exactly how much is the threshold. For example, the regulation says like the limit to be safe, this water is 15 microliters.
Yeah.
15 micrograms per liter.
Right.
Right. Can we detect that limit? I don't know if
For PFAS.
Yeah, for PFAS, for metals you are working.
Okay. I think I got the point. So you're talking about the correlation between the detection limit and the safety level for the drinking water. Is that right?
Yes.
Okay. So thank you. Well, it depends. I mean, for mercury, for cadmium, they have their own limit. I don't have the number in my mind for drinking water set up by EPA, and different countries have the different standard. But I do know for PFAS. Okay. So EPA currently classifies 6 different PFAS as a top concern in the drinking water. Among the 6, you have PFOA, PFOS, all containing 8 carbons. So for those 2, so EPA set up 4 PPT for drinking water at the moment. All right. A lot of people think this too much challenging to be detected, because even for the EPA itself, I'm talking about the verified method by EPA itself. This method 1633. They use LCMS method. They need pre-concentration method because they can never detect 4 PPT directly in that case, right? So again, I'm not sure EPA going to change the mind. Even less than 5 years ago, before 4 PPT, they said 0.003 PPT. That's even, I won't say that word, but you know what I mean. So, but back to your comments, why they set up 4 PPT for drinking water level? So mostly, based on the health or study. But if you ask me, do we have very solid medical evidence to show 4 PPT is really dangerous to health in drinking water? I cannot answer that questions. But I can tell you the current level set up by EPA is 4 PPT for drinking water.
Yeah, exactly. If 4 PPT is established for drinking water, so I can measure with the sensor, say, okay, this one has 4.
No, even for our sensor, we need concentrate first and then measure down to ppb. So we cannot direct measure the 4 PPT level.
Thank you.
Okay.
Yeah.
That's another thing. If you got chance to look at the paper published, some people from different technology background, if they claim they can do PPT or even below single PPT level, You probably want to pay a little more attention, go a little more detail about the technique. I won't say it's beyond that, but it's hard. It's really hard, okay? And why I'm saying that, this might be interesting to you and some other working in the field. You know, PFAS is sticky, right? It's like detergent, right? Stick to any surface. There is a one paper published to concern how sticky the all PFAS to different surface, metals, plastic, wood, whatever. So keep in mind, so PFAS sticky to all kind of surface. You can imagine if you have only PPT level in the solution, if you're trying to prepare a standard solution, maybe most of them to the surface. You have zero in the water. It happens, we know that, okay? So all this combined, so we need to be careful when we going through this kind of project. Maybe I say too much anyway, so.
That's the reason that like when people try to measure the contaminants in the water, like because the water, let's say in the river, you don't only have metals, you don't only have organic contaminants, you have a mixture.
Yeah.
Not correctly the correct approach for environmental purposes.
Yeah.
Make sure the combined effect of all.
Right.
And the presence of these because it's making it to extend quite the effect of other contaminants.
Yeah.
Say the
Right. Right. Yeah.
Okay. Well, I think we'll have to cut it off there. And let's thank Professor Zhang one last time.
Thank you.